Hi everyone, good afternoon. Thanks to be here. Today we are going to have a presentation doing by Oscar Beijbom from the UC Berkeley and the University of Queensland. And it's called Deep Learning in the Shallow Seas.
All right, thanks, Julie. So can you hear me all right? Yeah, okay. So I have a joint appointment at UC Berkeley Vision and Learning Center, so Machine Learning and Computer Vision Research Lab. I work with Trevor Darrell there. And here at the University of Queensland, I work with the Global Change Institute, OVU Goldberg, on the Catlin Seaview survey. I just want to quickly ask in the audience, actually, what you guys are working on, just so I know how to a little bit pose the talk. Could you just sort of quickly say what you guys are? Are you ecologists? Are you? Yeah, ecologist. Computer science. Any robotics? Any robotics people? Math, statistics. Awesome. Okay. Well, this talk is basically, the meat of this talk is about deep learning, so deep convolutional neural networks for image classification. So the goal here of this talk is actually really simple. It's simple to define, at least. So given an image and a row and a column location, the goal is to predict the benthic category. So for example, on this cross, the goal is to build a machine that can read this information and give the label, okay? So that's the whole goal. So why are we interested in this? Well, it is the case in marine ecology, as in many other sciences, that data is easy to collect and hard to curate, hard to annotate. So when these guys go out, the Catlin people go out, for example, oh, whoops, that was the wrong button. When they go out and survey the Great Barrier Reef, it might take a month or two to collect the images, hundreds of thousands of photographs. It actually takes 30 person years to annotate them manually. So it's basically a huge bottleneck between the knowledge and the image database. Okay. So let me just go back to this. So that just to give you guys a little overview for you who are not in ecology, the basic process is basically you take these sort of photographs, from the bottom of the ocean, and then you annotate them with these sort of random point annotations, so 50 or 100 points in the image. And the goal is to estimate a % cover of each image. You want to get a histogram of benthic substrates in each image, and then you can average that across your image database, and you can get a spatial map of your ecology. Okay. So how do we do this? Well, it turns out that computer vision is actually pretty difficult, right? So this is a famous XKCD comic, and give me ask me to write a web query. Sure, give me a few hours, but actually ask me to semantically interpret the image. Well, that's a lot harder. But what we're going to do, the approach we're going to do, is going to try and learn from experts. Okay, so we're going to build a database of expert annotations. We're going to set up a function, a parameterizable function, that is able to map pixels to labels. And then we're going to learn the function parameters from a database. Right, so far so good? Okay. So I've actually been working, I did my PhD at UC San Diego, and I did my PhD basically on this topic. So I've worked on it a lot. So I want to give a little bit of some background on how you might approach this sort of in the era before neural networks, and then look at how the game has changed with the networks. So that's what we're going to talk about. So if you think about these sort of images, benthic, ecological images, it's basically a texture classification problem. So there's previous work from 2005 that I started looking at when I started looking at this problem a few years ago. So I just want to walk you through that pipeline to give you some sense of what you could do. So if you have an input image like this looks almost silly, but this is this is actually the type of images that we're trying to classify. It's just a certain type of texture, like this is a sand texture, and I had other types of textures. So what I did is basically hand design this set of filters, a filter bank that you could apply to your image. Okay, so you apply this row of filters to your image, and you get this sort of output. Okay, and then you can apply each row in this filter bank, and you come up with a high-dimensional representation which contain the frequency components of the image. Okay, that's the first step. The second step then is to quantize these filter responses into an integer value. They call it a visual word. So they say if you have a certain filter response, well, let's cluster that so we associate that group of filter responses with a certain visual word. And after that, there's the third and final step. You just take a histogram of your whole image. You just count up the types of histograms, and that now becomes a descriptor for that image. And that descriptor is in a nice vector format that you can feed to a machine learning algorithm, typically a support vector machine, a random forest, a boosting framework, that kind of thing. So how do we adapt this for coral images? I mean, there's a couple of challenges, right? So how do we reconcile multiple adjacent textures in the same image? So for example, here, we're interested in classifying what's right here in the image. And it's a macroalgae, it's like a grass. But it's surrounded by this rock structure, right? So you can imagine if you look at a very, very small surrounding, you're not getting a lot of signal. You're just getting like a few pixels for it. But if you look at too big, you're just going to get this rock, right? So you have this trade-off between noise and context. And here's another example. If you look at, you need to have a big enough receptive field so you can capture the structures that are discriminative for this type of coral. And then the other thing is that how do we deal with color? So the previous work worked on grayscale, and how do we generalize that? So multiscale, we took a data-driven approach. So basically, sort of the simplest thing you can imagine if you're interested in this point, we pull the information at multiple scales around the image. So that's what we did for that. And for color, you can actually apply this filter bank separately across the different color channels. We use the LIB color space here. And then you basically cluster those responses instead. So does it work? Well, the database that we were working on at the time was it's a marine survey from Moorea. It's actual survey data about, they collect about 1,000 images per year, which is a fairly normal size image database. And we got around 83% accuracy on that database. And we thought, okay, well, that sounds pretty good. But a lot of these coral classes that you might be interested in is actually not that high. Okay. So I asked myself, well, it sounds good, but how good are the experts? What is good enough, so to speak? Okay. So the next step then was to create a proper benchmark data set. So we reached out to ecologists in the Great Barrier Reef, in Taiwan, in Moorea, that same group, and in the Line Islands. And we actually found surveys, actual ecological surveys, that had been annotated previously by the experts themselves. We then kindly asked them to sort of redo their effort on a subset of the images. And then we asked them to redo each other's work as well. Okay. And then we can finally run on the machine, and now we have something to compare against. So from now on, when I talk about accuracy, I'm going to use this measure called the Cohen's kappa for binary classification. So we're going to consider the binary classification task of coral versus other, or in this initial slide also macroalgae versus other. And the reason we use Cohen's kappa is because it's to balance out the fact that if you have 90% if you have 90% coral and 10% sand, you can do really well by saying 100% coral. That doesn't mean that your classifier is very efficient. So just to get around those sort of artificial biases of the raw accuracy, we're going to normalize it by this way. Okay. Okay, so if you just look at the experts, if you look sort of intra-experts, so self-consistency, and you look at the corals, or the red bar, you get around 90% accuracy. So that's actually really high. Collins kappa is not, this is not an absolute thing, but it's sort of how you can put that in context, these numbers. And then, interestingly, from this study, we saw that a lot of these other classes, the CCA and the TURF, were actually quite low. So the self-consistency even was lower than what you might expect. And now if you go between experts, then you drop further. So this is how well the method worked that we had previously. So, 60%, sorry, I keep pressing the wrong button. So 60% accuracy versus 90. So that was a little bit like a reality check that this method might not be ready to run sort of fully automatic in a robust way. Now it turns out there's other things you can do, right? If fully automated seems out of reach, maybe we can do semi-automated annotation. So we can very easily devise a scheme where you say, well, if the classifier is confidence, then you make a decision. If it's not, you just defer to the expert. Okay. So you could make this sort of trade-off plots where you show the level of automation and the accuracy. So this is again for this data set with these four locations: Moray Island, Heron Reef, and Nan Bay. And you can see the nice thing about these plots is that you start off really high here with this is fully manual annotation. You start off and you drop a lot when you go fully automatic, but it's relatively flat at the beginning here. So it turns out that even with this simpler method, you get about 53%. You can automate about half the work with very little loss in accuracy. So that was sort of encouraging, I thought, and we actually ended up building a system that we call CoralNet within the project that's in San Diego. So it's an online random point annotation tool, essentially, that is freely available, and it allows researchers from around the world to upload their own photographs, define their own label set, and then just sort of churn through the images using this semi-automated method. So it's meant to alleviate a little bit of the workload. And we have almost 5 million manual point annotations on the source and almost 200,000 images, which is pretty cool because it's a very diverse image set. It's from everywhere from the world. All kinds of cameras, all kinds of benthic substrate, all kinds of distances, and all kinds of label sets. Just a little short plug for CoralNet here. It is a random point annotation tool. It has this computer vision backend that we talked about previously. And it was also meant as a sort of Coral Ecology community builder where you can see what other surveys are in your area, and you can learn from that. Find collaborators and do meta-analysis and that kind of stuff. And then we have these modes of automation that's sort of the interface between the vision backend and the random point annotation tool. So the main designs, really quickly. So each project here is called a source. You can assign multiple annotators per source. Images and annotations can be easily browsed and searched. And each source has its own label set, but the labels are shared across the site. And each source has its own tailor-made version of the machine annotator. And the workflow is basically you upload images, you do some initial annotation, and then from that initial annotation, the machine will basically annotate all your images for you with a preliminary estimate. And then you can sort of iterate on this process and improve the backend and sort of do less and less of the work. Let me just click through this. Okay, so let me now switch to the actual main topic of this talk. I just wanted to sort of give that background as a contrast to what we're going to see in this part. Any questions at all so far? Okay. All right. So let me start with a brief introduction overview of how many here have used deep convolutional networks? 2 people? 3, 4? How many here have used any sort of artificial neural networks? Okay. All right. Well, okay. So if you go back to like Bishop's book on pattern recognition, artificial neural network was pretty much defined as a 3-layer network. You have an input layer, you have a hidden layer in the middle, and then you have your classification or output layer. And there's a lot of theory and a lot of analysis on that relatively simple network structure. Okay. So these are some of the ingredients so basically what I'm going to talk about today is convolutional neural networks. So the purest form of a neural network is fully connected. So you have layers which are fully connected. Every node is connected to every other node. So John LeCun pioneered this method of convolutional neural networks where you actually you're just locally connected between each layer through a little convolutional kernel that you slide across the image, which creates a nice translation invariant. So you typically have an input image, you have some sort of convolution, you have a nonlinearity, and then a pooling, and then a feature map, and then you can repeat this thing. So the convolution is the actual sort of the core of the poodle. This is the sort of equivalent to the filter bank that we looked at in the beginning of the talk. The nonlinear unit is basically to introduce a nonlinear component to your system, because if you don't, stacks of convolutions are all linear functions, and you can basically collapse that back to a single layer. So the nonlinear units are important, and there's been an evolution in the types of nonlinear units that people use. They started using sigmoid functions, but nowadays it's usually what they call rectified linear units. So you basically say if the activation of the previous layer is smaller than 0, you just set it to 0. If it's larger than 0, you don't do anything. You just leave it as it is. Okay. So there was this paper, 2012, which was very influential in computer vision, and they had a 8-layer network design called AlexNet, and basically achieved a state-of-the-art on the ImageNet. There's a big computer vision benchmark called ImageNet, and there's a recognition challenge each year. So they blew everyone out of the water with this network. And it's by today's standard, it's actually pretty shallow and pretty simple. But you basically start with your input image. You have an 11 by 11 convolution, a 5 by 5 convolution, and then 3 by 3, 3 by 3, 3 by 3. And then after this, you have 2 fully connected layers. And the motivation behind this is to build a nonlinear classifier, essentially, on top of the feature extractor. And then you have a classifier, linear classifier at the end. You can think about it that way. 2014, a team at Oxford designed this 19-layer structure called VGG, Visual Geometry Group. I think the name of the research group is by Andrew Sisserman. So now we have a much more complex structure with 19 layers. GoogleNet, later in the year, had this very sophisticated structure called the Inception network with now 22 layers. And then very recently, Microsoft Research came out with this structure called the residual nets. I can really recommend that paper. It's really impressive. They do get state-of-the-art on every single semantic computer vision task out there. Some of their networks are up to 1,000 layers. So it's pretty cool, I think. And here's just a sort of a schematic of how this has changed. You started with AlexNet, the first layer, with 8 layers. You got 16% error rate on ImageNet. So this is 1,000 semantic classes. You go down, and it sort of drops down further and further, and now we're down to about 3 or 4% error on this task. And these results up here are sort of before deep learning, the deep learning revolution. So the network we're going to talk about today, and that I'm going to use, is the VGG network, the 16-layer VGG network. It's been, I'd say, the most popular network in academia, because it's fairly easy to understand, it's fairly easy to modify and to tune for your particular task. So I just want to go through this a little bit more carefully than the other ones. So how many have seen this network before? Okay, so the same crowd. So here's the plan. We're going to take the image, and then we're going to, so in the input image has 3 channels, right, RGB, right? And we're going to run a convolution. We're going to run 64 3x3 convolutions on the image, okay? So instead of a 3-channel image, we now have this 64-channel filter response, okay? We do that, and then we do it again. We run another set of 64 3x3 filters, but now they operate, instead of operating on a 3-channel input, they operate on a 64-channel input. So actually, painstakingly did the math last night. I wonder if I can get it to show up. Never mind. Well, I just did the math on exactly how many parameters there are in these filters, and it grows rather quickly. I think there was maybe 2,000 parameters in this one, and then the 10,000 here, and then we're getting up to 100,000 parameters in the layers, next layers. So okay, but anyway, after these 2 first layers, you do a max pooling operation, so that you shrink the semantic spatial extent of the image. So now you're down to a 112 by 112 image, okay? And then you run 128 3x3 convolutions on that input. And right after you do that, you run another 128 3x3 convolutions. You max pool, okay? And now we're down here. It's 56 by 56, and now you run 256 3 times. You max pool, you're down here. You run, 512. You max pool, and now you're down here. So now you're down to a little 7 by 7 by 500 cube of data, okay? And then at that point, you apply this fully connected layers, which has this 4,000 components. And then after that, another 4,000 dimensional layer. So in this layer alone, there is 16 million parameters, because you're mapping from 4,000 to 4,000 fully connected. So you end up with 138 million parameters. And the way you typically use these systems is that you download the network structure, the definition of the network. You also download the pre-trained weights. So when I say weights now, it's the actual weights of the filters. So it's the shape of the filters. Okay, any questions on the VGG network? So these are some slides from Rod Fergus, trying to understand and visualize, get some insights into the type of stuff you learn from the networks. So the very first layer is these tiny little 3x3 RGB blobs or filters that operate on the image, and here you see like little image patches that give high response to these layers. So you see that it's mostly edges, simple colors, and so on, that activate this first layer. And the neat thing here is as you move up through the layers, it becomes more and more complex, right? So in layer 2, now we're looking at little circles, a little bit more complex edges, some textures, and so on. Here are some T intersections and that kind of stuff. You move up to layer 3, and now we're looking at wheels and round things, and here are some organic structures, and so on. So this is all stuff that gets captured by the network, And you move up to the higher layers, and now you have like neurons that basically react on dog faces and rather complex. Like there's a keyboard set of neurons, and there's several sets of face neurons that detect certain type of things. So there's a lot of there's just an immense complexity that's hidden among these all these network parameters. Okay, so let's see if we can do this for the Coral problem that we defined. So the simplest thing we can do is probably to just crop out 224. So this network is just sort of arbitrarily defined on a 224 by 224 input, and that was just how I defined the architecture, and that's the way the weights are given to you. So that's what you have to work with. Okay, we can crop it out. We can initialize the net with ImageNet weights that we can download, and then fine-tune on the interoperator data set, the one that I talked about previously. So this is what happens. So going from 90% self-consistency down to 85% between experts, we had about 60 with the old system, and now we're back to 78% accuracy. So that was really cool. And the other cool thing is that this took me about 3 years to do, and this took about a week to train. So it was sort of it's a little annoying that it worked so well, but anyway. And the accuracy, of course, depends on the data set. So for these data sets, so I didn't give you all the background on these data sets, but Moorea and Line Island are just higher quality images, higher quality survey images, better lighting. So you actually, on average, you get an automation level of 80%, and I've included the old system here just for reference. And it looks like for the Moorea data set, you can actually run this fully automatic within the acceptable margin of error, which is really cool. Now, if I'm just sort of zooming in here on the first two, I'm just zooming in on this top part of the graph. You can see that we start. You see something kind of interesting. You start with about 91% accuracy for Moorea, okay, and this is fully manual, all expert annotations. And then as you start mixing in really confident machine predictions, you actually go up instead of down. So you go up about 1% higher than what you started with, and then at the end you plummet down. Okay, but at this operating point, we're now around 70% automation, but we are getting higher accuracy than we got when we did everything manually, which seems, sort of counterintuitive. How is this possible? I mean, we're training a machine on expert annotation. So how can we do better than the expert? Well, I don't think it's actually that strange when you think a little bit about it. The simple answer is that we all make mistakes, but for different reasons. So you have a human annotator churning through images. You're going to suffer all kinds of sort of random errors. You lose focus, and there's all kinds of biases that people study in psychology. For example, recency bias. If you use the label recently, you're kind of more inclined to use it again. And there's a bias towards using labels that you like. If you like certain types of corals, you're a little bit more likely to use those. So. And of course, the nets will have their own problems, but they are sort of uncorrelated with the other ones. So by rejecting the confident automated annotations, we avoid some of the human errors, and we get a better system. And I'm going to guess. So this is all done post hoc, right? This is all done in post processing. But if you imagine an applied system where the user actually only did 30% of the work, you can imagine that the quality of that work is higher than if that user does 100% of the work, because you just have a little bit more time. Okay. So I was curious about this. I actually took a closer look. So at this 70% automation, we found 16 human errors were avoided, and 8 errors were introduced. Okay, so we won. The test set here is 2,000 point annotations across 200 images, so it's fairly small. But there's this gap of 8 images. And I connected back with the original expert who did the annotations, and I showed him, so this is what you did first time, this is what you did the second time, this is what the machine did. Can you maybe help me understand what's going on? And in both situations, in both the errors that were avoided and the errors that were introduced, about half were sort of ambitious. It's hard to tell what was going on because of image resolution, label set issues. And the others were just real actual errors that either the human made or the machine made. So here are some examples. The ones that are classified as human errors here. So the ground truth, and with ground truth I'm simply saying the first time the expert annotated the images, that's what we're going to call the ground truth. The second time, the manual annotation, he said sand. And then the machine said Porides, which is this coral. And of course, if you look at this point, it's just simply ambiguous. The point is right on the border, so both are okay. Here are 2 other examples where the ground truth said macro, this little patch of, it's hard to see on the projector. The expert said Porides, which is this colony. And the automated system said CCA, which is another type of algae. So on inspection, both of these could be correct, but this one is certainly wrong. It's just a random error because maybe it didn't zoom in far enough or stuff like that. Here's a similar type of error where the second set of annotation labeled it as this coral, which is in fact wrong. It's just off to the side. On the other side, we have these machine errors. This one was interesting. So the correct here is Porides, but the automated system said Millipora, and I think, at least according to the ecologist that did this, he said it's actually pretty hard to distinguish these 2 classes in this particular part of on this reef. Here are some cute errors. There's this little bit of algae sticking out in the coral. So he said macro first time, he said turf the second time. Those are both types of algae, but the network said pavona because it's a lot of the pavona coral around it. And similar here, or here is an ambiguous one where it could be sand, it could be across this coralline algae, or it could be this Montipora coral. So I thought that was pretty neat. We can actually go back and look at exactly what happens. And again, it is actually the case that the joint set of labels at 70% automation is better than the manual set of annotations. Okay, so far we haven't really done that much research in computer vision. We just sort of downloaded these ImageNet weights and we fine-tune them for our particular application. So one thing we can look at is that the initialization of the network turns out to be quite important. So it's sort of common wisdom in the vision community that if you're going to use these deep nets for a new task, you very rarely want to start from scratch. You typically want to copy the weights and start from somewhere, because they're so complex, because they have such high capacity. It's better to, you end up in very strange local minima. It's hard to avoid local minima if you don't do that. So we played around with thinking, can we make a better initialization? So the idea was to use the CoralNet database that I talked about earlier, so the user supply database, to make a sort of a CoralNet base net, which I'm going to call CoralNet square. So I took images from these locations, user supplied images from the site. And here's just a scatter plot showing the type of the diversity in terms of sizes and scales of the images. And of course, I didn't include any data from the multi-operator study. So this is all other type of coral data that's out there. And just by doing this, now doing the exact same type of training which I did here, we now get not a ton, but we get 2% for free by just using a better initialization. So at training time, in fact, it's more than for free. This this network is much easier to train because I'm starting from a network that is sort of used to seeing corals. So the whole weight structure is adapted to textures and corals, and now I can start from there and get higher accuracy and get it quicker in fewer iterations. So that was neat, I thought. And this difference actually increased when I have less data. So I ran an ablation study where I trained on fewer and fewer images from these 4 locations. And so at the end, you have this error or difference in about 2 or 3%. But at the beginning, we have, say, 100 training images, which is about 1 week's worth of annotation work in this situation. You know, the difference is actually 5%. So it's actually a pretty big difference. So when you imagine deploying repeated surveys across, you know, spatial, temporally, you know, this becomes important. Okay. Yeah, so I want to show some snapshot results on another type of data, because we've been banging on the same data set the whole time. So, like I said, I work with these guys from the Catlin Seaview survey, and we actually published this paper recently showing that you can take images from various parts of the Great Barrier Reef, and so they have this nice underwater scooter type structure, and you crop out little sort of fake quadrats, or just like artificial quadrats, and then you can classify them. So sort of straight out of the box, running the deep nets versus the old system, we got so the error here in terms of, so far I've talked about accuracy. Now we're talking about sort of the actual estimates of composition, so benthic composition. So the errors here, average error across a certain number of test sites. For turf, the average error using the old system was about 2 or 3%, and now we're getting down to about 1% with the deep learning method. So SVN here represents the old system, and DL is the new one. So I thought that was pretty neat. Again, there was really no iterations here. It was just taking that same training set and running it through. And on the right-hand side is a scatter plot of estimated covers versus the observed covers by a human expert. So with the old system on the right-hand side, there is, for certain substrates, it's not really, you would want the estimated slope here to be 1, the correlation to be 1 between observed and estimated, but it's sort of off on a couple of substrates, but it looks much better when you run it through the network. All right, so that's pretty much it. I just want to very briefly mention this if you guys are interested in playing around with this. There's this, you can, the what? Oh, perfect. There you go. So you can actually, so far I've talked about the networks in terms of a fixed input size, right? This 224 by 224. So these guys from Berkeley realized, and it's not, it's sort of reinvented technology that hadn't been used in a while. Realized that you can turn the whole network, if you turn the whole network into a convolutional structure, there is really nothing preventing you from increasing the input size. So you can go, instead of going from an input image to a scalar label, you now go from an input image to an output label map. So you have this nice function which takes you straight from an image RGB space to a semantic label space. And that's sort of, when this paper came out, I think a lot of people were just amazed, because this problem has been so difficult to deal with in computer vision. Imagine you have a whole image and you want to assign a label to every single pixel in that image. There's just been a lot of work on using conditional random fields and various types of context approximators and various sophisticated machinery And now this guy said, well, actually, just take your network and train it end to end, but show it, you know, images and show it these pixel maps, and the network will find that mapping for you. So here's an example of how that looks for one of the data sets that I work on. So you have an input image, and basically using a modern GPU, this took me, I can't remember if it's 1 second or 2 seconds, to label 4 million pixels with an accuracy that is not quite as high as if you sort of crop out and focus in on every single patch, but vastly superior to anything that were available before the neural networks sort of arrived. All right, so deep learning works. It's really fun to play around with. Data matters. So does initialization. And I have a feeling that what started us, when I started this project 5 or 6 years ago, what seemed like a complete dream, that we actually reach human level accuracy with these systems, I think it might actually happen pretty soon. So these are all people I work with at UCSD, the guys that helped me develop CoralNet, Stephen and Devang, and the guys at the UQ, Manuel, Alberto, Nove, and Trevor at UC Berkeley. So thanks for listening, guys. Yeah, so I think we have some time for questions.
We have 10 minutes.
Okay.
There is some questions?
Have you compared the pixel label accuracy to the patch label accuracy?
Yeah, so I typically lose. So I remember on that particular benchmark, we got like 81% with the patch net. We got 77 if I trained it fully convolutionally and run it fully convolutionally. I got about 79 if I trained it in the patch mode, but evaluated it fully convolutionally. So what happens is when you run these fully convolutional models, you basically end up sliding these convolutions over the image, but because you're subsampling all the time, the convolutions in the higher layers end up having pretty large strides. So your final output map is pretty coarse, so you get some interpolation problems. So there is a little bit of a trade-off, and there's been sort of feel like new papers come out every week, but there's various ways you can try and remedy that by changing the structure of the network a little bit. So, yeah.
Just in your original data sets, I was just wondering, those row column points that were then marked by the experts, how were those points chosen? Were they just sort of, did they mark like lots of points on each picture, or were they kind of randomly chosen, or were they
chosen? They're randomly chosen.
Okay.
Yeah, so I sort of left out a couple of those sort of coral context slides, but it's a random sampling design. So the images themselves are selected randomly across the reef, and then the points are selected randomly in the image.
Okay.
And the reason you do that is because all you're interested in is an unbiased estimate of the percent cover.
So the typical points, like when it was a small algae surrounded by coral, that was just by chance that they were.
Yes. Yeah. So I mean, in the Morea data set, there's 1,000 images. Each image actually do 200 points. So there's 200,000 point annotations. There's a lot of labor goes into these things. So.
Another one?
I was looking at the graph that you're showing, comparing the different nets, and you started with the very shallow ones and you ended up with the impressive ones at the end.
Yeah, the residual nets.
So what's the research pointing out at the moment? Because it seems like it's reaching kind of like a plateau in the error, just because you're getting very complex.
Yeah, so it's down to the image net. So ImageNet have 1,000 semantic categories, and they are very detailed.
Yeah.
So when they talk about error on that data set, they talk about the top 5 error. So it's correct if it's if any of your top 5 predictions is the correct one.
Wow.
But still, that accuracy is actually higher than a casual human observer, right? So if you just ask an average human to classify images, you're going to do worse than these nets. So yeah, at some point you need a more challenging benchmark. Yeah. But as far as I'm concerned, as far as just classifying images, the problem is basically solved. Yeah. I don't think you can do a lot of interesting research by just sort of classifying images. Now, detecting parts in images and like segmenting them is more challenging. And a lot of people in computer vision now are starting to get interested in interactions between language and images. So generating captions and trying to capture that interface between language and images.
Wow.
Yeah. But it was pretty surprising. I mean, before the residual nets came out, these 16-layer nets seemed insanely deep, and I think no one was really bothered. Like, I mean, that seemed enough. But then, yeah, it wasn't, turns out.
One more question? I have one. Can you have an over-parameterization in your network?
A what, sorry?
Over-parameterization?
Yeah, I would say they are over-parameterized. You mean like redundant parameters? Yeah. I
can bring noise at the end or something like this.
Right. So, that's an excellent point. I mean, the only reason, there's a couple of reasons why this works. So you have a network with 140 million parameters. You're going to have a huge risk for overfitting. You can basically on a small data set, you can basically memorize your whole training set, and then you have no generalization, right? So a lot of the games when you train these networks is about holding out data and making sure that you don't overfit your training data. So you always have to look at, if you run the networks too long, you're going to start doing worse because you're becoming too specific. So they all have too high capacity. And that's why it's so important to start with ImageNet, because on ImageNet it's strong enough that you can actually regularize them and give them a good initialization. So that's all sort of how that fits together. Does that answer your question?
Mm-hmm. And why Morea is reacting differently like from the other data sets?
So Morea and Line Island both sort of roughly the same trend, and they're both captured. They are very careful. The ecologists that capture them are very careful about the distance to the bottom. They're very careful about the lighting. The other two data sets doesn't have any artificial lights, and I think just lower quality cameras. But it can also have to do with the ecology. A lot of these things are hard to compare across data sets, because I think in the Taiwan data set, you just have difficult categories to separate out.
More species.
Yeah, more species and lower quality images and also a smaller training set in that case. So it's a number of factors that you have to take into consideration. And that was why I was so relieved when we worked on the Catlin data, because that was just sort of a new type of data, and it sort of seemed to generalize pretty well to that. Okay, well, thanks so much for coming.
Thanks, Oscar.
Yeah.
Thank you.